Hi everyone, my name is Havan Fu from India. Today I would like to present my paper, Maximizing Computing Accuracy on Resource-Constrained Architectures. The work has been done by Van Fu and Professor Olivier Sontier. So today, the increasing demands for computing power and accuracy in various fields, such as machine learning, big data, autonomous vehicles, lead to the development of resource-constrained architectures. And energy is one of the most important ingredients to power up the embedded devices and also maintain the performance of computing operation. As the complexity of application grows, designers need to fit more computing kernels into a very limited code budget. This poses a critical challenge for energy-efficient computing. The resource-constrained architecture here can be for example, the embedded system, mobile devices, and IoT devices with very limited computing resources. For example, memory, energy. So it makes it challenging to achieve high computing accuracy. So fixed point arithmetic is an energy efficient solution for many applications in embedded system, like FPGA, ASIC, and DSP system. So generally, fixed point representation is a way to encode the real number. So it has two parts. Integer word length is responsible for covering the dynamic range of the number, and fractional word length provide a minimal numerical accuracy. Word length optimization is a process of determining integer word length and fractional word length for every variables in the application to satisfy the cost and accuracy requirements of the system. Some studies show the uniform word length where the word length of variables are the same. However, the current approaches focus on multiple word length optimization to obtain more energy saving from accuracy and cost trade-off. And in this study, we focus on solving fractional word length optimization, which involve finding the best word length configuration for the fractional part. Fractional word length optimization is an NP-hard problem because the complexity increases exponentially when increasing the number of variables. So from now on, I use the term word length optimization at the meanings of the fractional word length optimization in my talk. So resource-constrained architecture can present a significant challenge for achieving high computing accuracy. For example, IoT devices may struggle to produce high quality output due to the limited energy or area budgets, while a high-performance computing system like the servers with a larger cost budget can handle the task with ease to produce a high-quality output. So the question here is, can we improve the performance on resource-constrained devices by applying resource-constrained word length optimization? So if we can do that, this is a big deal, because it allows us to maximizing the computing accuracy on resource-constrained architecture, unlocking many possibilities for high-performance computing. For example, in machine learning, image, speech recognition, and autonomous vehicles. So this is where the concept of resource-constrained word length optimization becomes important, because it can help to maximize the quality of computation under the cost budget and improve the competitive advantage of the electronic device manufacturers. So in this slide, I show you the mathematical equation of resource-constrained word length optimization. So here we have a vector W representing for the fixed point word length to be optimized. So we need to maximize the accuracy lambda W under a given cost budget C budget. To illustrate the potential of resource-constrained word length optimization, we look at a specific example, a FIR filter with 17 variables to be explored. Using a random search, we explore a subset of the solution space, evaluating each solution output accuracy at PSNR and energy cost in nanojoule for a random work length configuration. The red line here on the graph represents a maximum energy cost batchist at 0.0075 nanojoule. And you can see here there are a large set of the solution that consume the same amount of energy as the cost batches, but result in significantly different output quality, ranging from minus 20 dB to 40 dB as the accuracy. So this is a big room for exploration. For example, here the point is circled by green could be the solution we want to find. So in this slide, we illustrate the limitation of classical methods in addressing the resource constraint work length optimization problem. As a typical example, we consider table search, a state-of-the-art approach in this field. Table search is an integrative optimization algorithm that starts from an initial solution and progressively improve the solution by searching the neighborhood for the better ones. However, the quality of the solutions obtained with table search strongly depends on the starting point. This limitation of the classical method motivates the development of new approaches to provide more stable and efficient solution for the resource constraint work length optimization. So in the next slides, we will present our proposed approach based on Bayesian optimization, which outperform the classical approach like table search in terms of quality. The key idea of our approach is to apply Bayesian optimization, a technique for optimizing the function that is expensive to evaluate, that is commonly used in machine learning and optimization problems. So our approach, we explore the variable as a work length for the resource constraint work length optimization problem. These techniques allowed for global search to avoid local minimas. We provide a loss function that adapts the work length as a variable to be explored. We use a tree structure pattern estimator, TPE, as the Bayesian optimization algorithm in our approach. So TPE construct a probabilistic model based on the past sample to suggest new points. At the iteration case, TPE can separate the known solution in history in good and bad group based on the loss value. Assume that we have n work length variable to be optimized, and we call VK is one of the n work length variables. So we separate the work length value of the VK from the sample solution into LK and GK, where LK is a set of the work length value of VK in good group, and GK is a set of the work length of value of the VK in bad group. TPE use the two sample groups to model two likelihood probability density function, Lx and Gx in the figure here. So then it selects the next solution by maximizing the ratio Lx over Gx, which means that the selected point had low probability of being bad solution and high probability of being good solution. So the benefits of TPE is to search globally and likely to avoid the bad local minima. So in this slide, I present the loss function in our approach. The Lagrange multiply approach is used to convert the constraint problem into unconstrained problem. So alpha is a parameter that controls how much the search process explores a new solution versus exploit the known solution. So if alpha is more, the algorithm will prioritize exploring high-quality solutions over the cost constraint. If alpha is large, it will prioritize finding the solution that fit within the cost constraint, but may not be the highest quality. So in order to find a solution that satisfies the cost constraint with high quality, we focus the loss function to cover only the narrow range, CL and CH, around the cost budget. The solution with the cost outside the range will penalize with the positive infinitive loss. By doing this, we ensure that the search algorithm focus only finding the solution that have both high quality and satisfy the cost constraint. For the evaluation, we use filter, FIR and RIR, and non-local means, a noise reduction algorithm using image processing as a benchmark of our approach. We use different energy consumption targets at the cost budget in experiments. FIR and RIR filters have 17 and 33 variables to be explored. Non-local means has 19 variables to be explored. So we have compared the performance of our approach with uniform work length optimization, a simple and fast method considering all the variables having the same work length. This figure represents a performance comparison between our approach and uniform work length optimization in terms of the quality of the results for different benchmarks. The results are normalized with the highest quality value indicated in the parentheses for each benchmark. So here in our approach, we parameterize the alpha from 0.1, 0.2 to 0.5. So the graph clearly shows that our approach outperforms uniform work length optimization in terms of quality of the results for a given cost budget. We can observe that the solution obtained by our approach with different value are always better than those obtained by uniform work lengths. This indicates that uniform work length may be able to quickly obtain the solution, but it is not optimal. Our approach, on the other hand, is able to provide significantly improved solution in several cases. The solution quality found by our approach for those benchmarks can be better than uniform work length from 30% to 300%. So, in this slide, we compare the quality solution found by our approach and troubleshoot for different benchmarks. In this comparison, we synthesize the solution obtained by varying the starting point for troubleshoot. On the other hand, for our approach, we summarize the solution obtained by using different alpha values. For example, alpha is 0.1, 0.2, 0.3, 0.4, and 0.5. The figure shows a clear difference in stability of solution obtained by the two methods, while the solution found by troubleshoot strongly depends on the starting points and can vary greatly in quality. The solution obtained by our approach is much more stable. The average quality of solution obtained by our approach is consistently better than though by taboo by up to 170%. In conclusion, the resource constraint work length optimization problem is an area that has been lacking study. Classical approach have proven to be limited in addressing this problem. Therefore, we propose a Bayesian optimization-based approach to tackle the issue. Our approach significantly outperforms classical approach, and it is the first efficient approach for this problem. However, there are other aspects that need to be explored, such as scalability and optimality. Thank you very much for your attention.